Good morning, everyone. So today we are pleased to welcome Lars Blatny from ETH Zurich and the Snow and Avalanche Research Institute from Davos. And Lars completed his PhD at EPFL in Lausanne. And he will be around this afternoon. So if you'd like to speak to him, don't hesitate to tell me. And I think that you can go ahead, Lars. Thank you.
Perfect. Yeah, thanks for that introduction, and thanks a lot for having me here. I'm very excited to be here. And the plan is that I'm also coming back later this fall and staying for a longer period of time. So I hope to get to know you even better then if you don't have time to chat with me today. Today, I will give a little talk on the modeling that we've been doing back home in Switzerland for modeling granular media and their flow using a numerical method called MPM, material point method. Just before I begin, to give the proper acknowledgements, most of what I'm presenting here today is work I've done together with Joan Gomme and our lab at Davos and in Zurich. This is our group picture right here. Also, I was co-supervised by Professor Molinari at EPFL during my PhD, which I finished 1.5 years ago now. Later in the presentation, I'll also show work that's been done together with Nico Gray at the University of Manchester. We're standing here in front of what was a rock avalanche in the village of Brienz in Canton of Graubünden. This is the kind of alpine mass movements and, let's say, granular flows that we're interested in modeling. There's a great interest from the Swiss cantons in having predictive models to understand these processes. And this is the village of Brienz that fortunately was not taken by this rock avalanche. As you can see, this is what happened about 2 years ago on the picture we were standing on this road right here. Personally, I'm more interested in snow avalanches, not because I like the winter and I like skiing, but because I think snow is a very interesting material. It's in a way a perfect example of a natural cohesive granular media, at least when it starts to flow like an avalanche, as we can see here. This is some avalanches that were triggered artificially in Valais in Switzerland. What's also interesting here is also to look at the triggering mechanism, the crack propagation that leads to the avalanche to start flowing. That's not something that I will talk about today. I'm more interested in, let's say, the granular flow part. So here we see like the crack propagating. It's also very interesting. When the second avalanche is released here, you clearly see it sort of propagates along the whole ridge here before it starts flowing. It was triggered by a helicopter that dropped a bomb, yeah. Snow is a very interesting material, as I said. First of all, it's a very hot material, perhaps counterintuitively, because it lives so close to its melting point in its natural state. It is, of course, a solid, a porous, brittle solid. If you will, snow on the ground has a certain microstructure. This microstructure may also evolve over time because of metamorphism, which follows from the fact that it lives so close to its melting point. It's not just a hot material, it's also creepy. It can show these very slow viscoplastic deformations, as we see here. And finally, it is a granular fluid. A highly compressible and cohesive granular fluid. Here we see a snow avalanche from the top, and you can clearly see those granular structures. Here there were some snowballs formed in a tumbler. I see clearly a granular material, and it shows also these well-known, let's say, granular phenomenon like levee formation, fingering of the material, and also surface waves. Highly compressible because we can see quite large variations of density within the flow. So the question for us is, how do we model this material in a unified way, and especially how do we model it as a highly compressible and cohesive granular fluid? This is also a question that the more fundamental researchers are also asking themselves. And that's also why I'm here to learn from you guys. So that is basically the motivation for our research and this talk. The next point that I'm going to talk about is the numerical scheme that we're using to model such materials. Then I will give a brief introduction to the framework of finite strain elastoplasticity, because this is the framework that we are going to model our constitutive laws in. For those with a solid background, this might be very familiar to you guys. For those who have a more, let's say, fluid mechanics background, this might be new, so I want to try and make it accessible for all of you. Then I'm going to talk about the particular model that we have come up with, which is then formulated in the framework of elastoplasticity. So what is the material point method, or MPM for short? This is the numerical scheme that we are using because it's really great at modeling extreme deformations of solids, also as it transitions into fluid behavior. And so historically, this is typically attributed to Deborah Sulsky and her coworkers from New Mexico in their 1994 paper, but you can also see it as an extension of previous methods, in particular particle in cell methods and the so-called fluid implicit particle method from the 80s. Yes. So in that sense, you can say it goes all the way back to Harlow in the 1960s, actually, if you think of the particle in cell methods. And it's actually conceptually quite simple. You just discretize your material domain with these material points or Lagrangian particles. And then in addition to that, you have a background grid that facilitates solving the momentum equation in a FEM-like way, so just like in the finite element method. So here I show you basically the simple discretization of the momentum equation, here just assuming an explicit time step, and then you have the forces, internal forces from the stresses, and the forces of gravity. So that's conceptually how it works. Let me go a little bit more into the details of the algorithmic steps. So the first step is to take all your particle quantities and interpolate them to the grid. So here you see I find the mass on the grid node I, velocity on grid node I, and forces on grid node I from the particle quantities, mass of the particle, velocity of the particle. The mass of the particle is constant, so mass conservation is automatically fulfilled. And this is just basically an interpolation step. Then we do the actual update of our velocity and grid positions. Here, just assuming an explicit Euler step, a forward Euler step, or if you will, a symplectic Euler step, because in principle I'm using here the updated velocities to get the new positions of the grid. Then, when we've done that update, we interpolate back to the material points in a similar kind of interpolation. Now from the grid to the particles, we get the new positions, the new velocities, and also the deformation gradient. This is something I will come back to later. So basically a measure of the strain, which you can then use to find your new stresses and therefore the grid forces. And then finally, you reset the grid. So in practice, you don't need to do this step because you actually didn't really update the grid in the first place. This was just a computational step, let's say. So what are the advantages of doing it this way? Well, the main advantage is you don't have any mesh distortions if you're thinking in terms of the finite element method. That is, let's say, the primary reason that we're doing this. We don't have any issues with mesh being distorted because there is no mesh in the first place. It's just this background grid that you need for computational purposes. Mass conservation is automatic and therefore trivial. You don't need any special treatment for the free surface due to its, let's say, Lagrangian nature. And something that's also very important for us, modeling natural hazards, complex terrain, is easy to include. Erosion and entrainment is also something that can be explicitly simulated by just putting material on your bed, and I will show examples of that later. Now, there are also disadvantages, the obvious one being you need both the particles, the material points, and the grid. So it has a larger memory footprint than other methods, perhaps. Numerical dissipation is also an issue. At every time step, you need to interpolate between particles and grid to particles. So it means that in principle, if you start decreasing your time steps, you might actually get worse results because you have induced more dissipation. To show you an example of that, here we see granular collapse, or just a column collapse, using different transfer schemes, so different interpolation schemes between the grid and particles. And you see here, if we use the earlier methods, we see, first of all, even with this method, we don't really get a nice collapse. But if we decrease dt by a factor of 10, I know it's very small, but it's a decrease of dt of a factor of 10, we don't really have any collapse at all. If we use the newer methods, we see between these two methods, which are affine transfer schemes, so they conserve affine velocity fields. And that makes the equations that I showed you earlier a bit more complicated, but the principle remains the same. You see that those remain fairly similar. If I decrease dt, at least for the newest schemes that we have today, we don't really see much of a difference. So we have reduced our numerical dissipation quite a lot. Then my second point here was no hard boundaries, in the sense that we apply our boundary conditions on the grid, but because of the influence of the interpolation functions, they have a certain support. So if I apply the boundary condition on the grid node, it will still influence particles further out. So if you have a shallow flow, for example, this could be a problem, but it's something that will vanish with convergence of dx. Convergence, error, and stability analysis is difficult compared to FEM. For example, in terms of the quadrature error, we can say that MPM is basically the finite element method, where the integration points are the moving material points, and the integration weights are the volume of the particles. So that means that our integration is less exact than in FEM, and the problem can also be that we have sort of agglomeration of material points in certain regions, which will make our numerical solver less exact. But there are also new schemes that seem to correct for this, having material points agglomerating in certain points. So there's a lot of work going on in the field. It's a very active community. If we think historically, the first MPM schemes were using these linear hat functions for interpolation, like in typical linear FEM. No one is using that anymore because they realize that it can lead to what's called cell crossing errors. So when particles are moving from one cell to another, you can have some instabilities. So there's a lot of movement in the community, and a lot of these disadvantages have also been addressed. Okay, that was what I wanted to say about the numerical scheme. Now, the framework in which we are formulating our constitutive laws, which is elastoplasticity. Now, for those of you with a solid background, I don't know, like if you have mostly fluid backgrounds or solid backgrounds, so I don't know exactly the level at which I should frame this, but I'm going to sort of go through the main steps of what I call finite strain elastoplasticity, which is, the first step is decomposing your measure of deformation. So you have your deformation gradient, and you assume a multiplicative decomposition of this deformation gradient into an elastic part and a plastic part. And for the velocity gradient, you also have an additive decomposition of the elastic and plastic part. For the elastic part, it's fine. We can have, you can choose your elastic model. Here, very typically, we are using Henke's model. It's a very simple, hyperelastic, isotropic frame in different elastic model. It's basically the small strain relation that you know, but instead of having the Cauchy stress, you have the Kirchhoff stress. And instead of having just the small strain tensor, you have the what's called the Henke strain, so the logarithmic strain, if you will. Now you have the elastic model. You need a yield function to determine the onset of your plastic deformations. So it basically defines a set of admissible stress states. Here I just show you the very well-known von Mises yield surface, which is a cylinder in principal stress space, and we can only be inside or on this cylinder. These are our admissible states. And you can frame different yield functions, which will become clearer later. It's not enough to just say this is my yield surface in stress space. We also need to impose other conditions on the plastic deformations, and that's through what we call the plastic flow rule. And it essentially tells you that the plastic rate of deformation should have a certain form, and we need to choose what's called the plastic potential function. So this essentially just says that this tensor has a certain magnitude in a certain direction, which is given by the plastic potential function. It's nothing more complicated than that. Very often, this G is just chosen to be equal to the yield function. That gives us an associative plastic flow rule because it's associated with the yield function. And mathematically, this means that you are maximizing your plastic dissipation. Obviously, the introduction of plasticity can only decrease your energy. That's thermodynamics, right? And if you want to maximize that, you choose what's called an associative plastic flow rule. There are certain conditions you need to fulfill. I will not go into details here. One of them I already mentioned. You can only have admissible states within the yield surface. And then how do you solve these equations? You can do what's called an elastic predictor plastic corrector scheme. So you assume that all your deformation is elastic. Then you check if you violated your yield criterion, and then you project back to the yield surface. And that's essentially this equation here. If you use the Henke's model, it becomes a quite simple equation like this. Even though it looks simple, it's actually quite difficult because the problem is if you have an elastic step that's right here, how do you project that back to the yield surface? And if you have a complicated yield surface and a complicated plastic flow rule, this can be numerically at least quite difficult to accomplish. So that's, in a nutshell, finite strain elastoplasticity. We could spend hours talking about this, of course, but this is the framework in which we want to formulate our constitutive law. Now, just to give some examples of that, if it wasn't fully clear from all the equations and text on the previous slide, you probably know the Drucker-Prager model, perhaps, which is a cone in principal stress space like this. So this is our yield function, our yield surface. It's a smooth version of the more well-known, perhaps more Coulomb law. I can, instead of drawing it in this principal stress space, I can draw it in terms of these two elastic invariants. My P here, the end of the bracket is not shown here, but this is essentially the trace of the stress tensor. And here we have Q, what I call the equivalent shear stress. So tau here is now the deviatoric stress from the Kirchhoff stress tensor. Now I have written here my yield function. What about the plastic flow rule? So this is the equation that I showed you on the previous slide. If I assume an associative plastic flow rule, I replace my G with Y. So Y is here, my yield function. I can do the math, and I can get this as my plastic flow rule. This is interesting because if we want to look at, for example, what is the change in plastic volume, we can just take the trace of this rate of deformation tensor. And we can see that if I take the trace of this, the deviatoric stress tensor falls out, and I am left with a quantity which is always positive, because gamma dot here from the previous slide, if you remember, has to be positive. That's the Kuhn-Tucker condition. And that tells us that whenever we have a plastic deformation, we're always increasing the volume. And that's why very often people are using a different plastic flow rule, for example, by just using Q here instead of this part, right? So this is sort of things that you need to take into account when you're formulating plastic flow rules and formulating your yield surfaces. Here is just an implementation of that in MPM. You see I increase my friction and I get a smaller run out of my column collapse. We can introduce cohesion here by just shifting the yield surface. That means I'm allowing for some tensile states. So this is compression, this is tension. We can implement that in MPM as well. You can see clearly these cohesive features as I increase my cohesive parameter here. It's, as you can see, it's not perfectly symmetric because my material points are sampled randomly. So you see some deviations from symmetry here. Now let's make things even more complicated, and let's talk about elasto-viscoplasticity, which is when we impose, or at least in the context of overstress models, which or in the context of what Piotr Brezina formulated, we impose our plastic rate of deformation, let's say, instead of having it to be something that we calculate as the projection to the yield surface. So that means we are no longer respecting all these Kuhn-Tucker conditions because we can in fact be outside of the yield surface, at least in the view of Brezina. And here we have some time parameters, so a relaxation time, a viscous time, if you will, that brings about the visco part in viscoplasticity. It's better to look at an example. So I choose now my yield surface, for example, to be of a von Mises type like this. So this was the cylinder in principal stress space. I plug all those quantities into my expression. I get this expression right here. I formulated eta now as a viscous parameter. I can rewrite this, and you see that this is essentially just Bingham. This is Bingham. Q is my equivalent shear stress. Eta is my viscosity, and gamma dot is my strain rate, plastic strain rate to be precise in this context. So if I implement that in MPM, you can see here what I get. I increase this viscous time, or I increase eta, the viscosity, and I see a more viscous flow. What is more interesting is to also visualize this plastic strain. Here you see a slowed down version of this. You see when we have no viscosity, these shear bands are very clear, right? But as I increase my viscosity, we don't really see these the strain localization as we can with the von Mises type model. Maybe I play that again. Oh yeah, so an example where we used this kind of model, well, we used not Brezina von Mises, which was Bingham, we used Brezina Drucker-Prager, as I showed you on the previous slide, but with cohesion as well. We used this to model slush flows in Alaska. They have a lot of slush flows in certain parts of Alaska. This is also what we presented at the International Snow Science Workshop in Norway. What is interesting also about this simulation is how we can, with this numerical scheme, also model entrainment and erosion explicitly. So here our bed is made of the same material as the flowing material. It has a certain cohesion, so it stays there, but as this flow is coming in, it will be entrained, it will start to yield, and we have a flow that's being entrained and mass accumulated. What is funny is it kind of looks like a discrete element method simulation, right? Because you see the individual particles, but it's actually a continuum model. Okay. So what about snow specifically? Now we talk generally about elastoplasticity. What about snow? We could use a Drucker-Prager-like model. This would be very relevant for granular materials, but for snow, we also know that it also not only fails in tension and shear, but it also fails under isotropic compression. If you compress snow, you will see it's going to fail, right? It's going to yield. So instead of having those kind of models, we use what we call the modified Camp-Clay yield surface. So here we have yielding both in isotropic compression with a certain pre-consolidation stress. I call it PC. We also allow for cohesion with a certain parameter beta. So that's our yield surface. What about the flow rule? We choose an associative flow rule. And doing the same kind of calculations that I showed you earlier for the Drucker-Prager, you can then deduce that certain plastic states will undergo dilation and other parts will undergo compaction, volumetric compaction. And we then introduce a hardening law. So that tells us how our yield surface is going to evolve with the volumetric compaction. So if we have compaction of the snow, our snow is going to get harder. We want to increase our yield surface so it gets stronger, right? And vice versa, if we have dilation, our material gets sort of weaker. We need to shrink our yield surface. And that's essentially what our hardening law says. So we can formulate that as a function of PC as a function of the solid fraction. Now there is a point here where we have neither dilation nor compaction. That's what we call critical state. And as our yield surface shrinks and increase, all those points will align on what we call the critical state line. I want to make this a little bit clearer by showing two hypothetical stress paths that we can impose in a triaxial test. So let's say we first isotropically compress our material to a certain point here. Then we start shearing until we reach the yield surface. We will have some elastic decrease of our volume perhaps. And you see here my shear stress is also increasing. Then because we are on this side of the yield surface, we're going to start having compaction, which means our yield surface is going to start increasing, but it can only increase until we reach a critical state. So at this point, our yield surface is going like this, and this is our critical state. This is the apex of the ellipse. And that's it. Then we're done. We cannot have any more increase or decrease in volume. But what if we take a different stress path? So we isotropically compress until this point, then we start shearing. We reach the yield surface as before, but now because we are on the other side of the ellipse, we're going to have dilation and we're going to have volume increase until we reach the critical state line. So in all cases, we are reaching a terminal state, which is the critical state, but the way we get there is different. So this type of model has been implemented in MPM, and we have used this to model snow avalanches. There is a problem with this, which is the fact that it's completely rate independent so far. So far, there was no viscosity in here. There was no elastoviscoplasticity. It was just elastoplasticity. This is a simulation, yeah. You can see the domain of the simulation is here if you look very closely, and then the rest is just a rendering. And this is triggered by a snowman that falls here.
So at the surface, all the balls or particles, again, it's a continuous.
Yeah, exactly, yeah. But yeah, as I said, it's completely rate independent. What we want is to model this as a granular liquid, at least when the avalanche starts to really flow. Because if we didn't have this, we wouldn't reach any steady state or anything like this. And we know there is evidence, at least in the literature, that snow avalanches, for example, will follow the mu of I rheology. So how do we include the mu of I rheology into our framework? So this is, for those not familiar, this is essentially the mu of I rheology, where the shear stress is proportional to the pressure, but with a friction coefficient of proportionality that depends on what's called the inertial number. So essentially how fast is the flow. So how do we do this in this type of model? What we can acknowledge is the fact that when we start to have a flowing state, those states will tend to align on the critical state line. So essentially what we just need to do is to make the critical state line dependent on the inertial number, just like in the mu of I rheology. You see here, this is again in the space of P and Q. So this is really our factor of proportionality. And it means that at critical state, we retrieve exactly the mu of I rheology. And this is the typical functional form that is used in the mu of I rheology. There are also other choices, but this is a typical one where mu increases from a lower value mu1 to an upper value mu2 asymptotically as you increase the inertial number. Inertial number is given by the intrinsic diameter and density of the grains, and also the strain rate and the pressure. Now, there is one problem here, which is the fact that we have cohesion, so we have negative pressures. That doesn't really go well with our definition of the inertial number. So what we do is we introduce the cohesive inertial number. This is something that has been shown before for cohesive granular media, where essentially we just add the cohesive stress, so this part here, to our inertial number, and we get the cohesive inertial number. So that's the, let's say, evolution of friction. What about evolution of density? We assume, for now at least, a very standard or simple evolution of density, which is well known in the slow compaction of soils, powders, and we've also shown it to be valid for snow. We do these kind of microstructural simulations as well to figure out what is sort of the evolution of density with pressure in snow. This is a little bit of a digression, but it is not the phi of I rheology that you might know. For those of you who are familiar with the mu of I rheology, there's also the phi of I rheology, where the solid fraction is found to decrease typically linearly with this inertial number. This is not what we are opposing here, but qualitatively at least, I will show you that we can get quite similar results as well. So here are the type of simulations that we are doing with our numerical model, collapse simulations, both with and without cohesion. So here you see clearly a different behavior when we increase cohesion. This is with beta equal to 0.3 if you were interested. And we try to also validate our model. So here you see the runout, as a function of time. So this is a front position of the collapse for different slope angles, comparing with some experiments that have been done before. What is interesting is also to look at the evolution of the solid fraction. So as the collapse start, we have this very sharp increase in solid fraction. This is just because I didn't let the system settle before I started measuring the behavior. But then as it has settled, you'll see that we will have a stronger decrease of solid fraction when I have a larger slope angle. So when you have a faster collapse, we have more dilation, let's say, which is also what the phi of I rheology should tell us, right? So that's interesting. We also try to validate towards the more recent experiments that have been done with these cohesive controlled granular media, so glass beads coated with polymer to induce a cohesion. And this is some of the validation tests that we are doing, again, comparing with what other people have done also here at the Institute. So here you can see a little bit what happens if I change different parameters, if I increase cohesion, have more cohesive behavior, more bigger blocks. Same with increasing the initial compressive strength. We can also retrieve the analytic solutions that we know from rheology during steady state flow. So if you have just a simple 2D setup like this, you can determine what analytically from the rheology what the velocity profile should be. Here I show you what sort of the measured velocity is on different slope angles. You see a pretty good match also with the analytic solution. So we're pretty happy about our model being able to really retrieve the rheology. There are other steady state solutions that you can find, not just on an inclined plane, but also if you look at flow over a bump like this. So these are experiments from Virolet and coworkers where they looked at flow over a bump like this. You see this very interesting steady state forming here. But if you have a different initial condition, like you place some material in front of the bump, you can get a completely different steady state solution forming. So our question was, could we also reproduce this with our model? I mean, it's just a qualitative test, but at least we are able to reproduce these two steady state regimes. This they call the jet solution, and this they call the shock solution. And then finally, as we progress, we are interested in applying this model to real events. I mean, as a group of alpine mass movements, this is sort of our job, right? This is the terrain of Vallée de la Sionne, which is a test site for snow avalanches in Switzerland that we operate, or that SLF, the Swiss Federal Institute for Snow and Avalanche Research, is operating. But we are also interested in seeing if, you know, this rheology that we are having here can also be applied to different events. You probably have seen this in the news. It happened about 3 weeks ago in Switzerland. A massive, massive rock and ice avalanche happened in the village of Blatten in Valais. And it completely destroyed the village. It happened on May 28th, so the Wednesday before Ascension Day. And it was about, I think, 10 million cubic meters of mass, so really massive. It happened by a rock slide or a rock avalanche that fell onto a glacier, and the whole thing released and went down. And one fatality, unfortunately. It was expected, so it was mostly evacuated. And so yeah, we're interested in also seeing, you know, can we model other types of natural hazards with our model. This is a simulation that we did. Here you see the actual run out of the event. And we can reproduce our runout very well, but of course this requires more analysis. So far we also can't really get the deposit heights to be matched with the observations. So perhaps other rheologies are more relevant for this, or perhaps there are also other events that occurred. I mean, there could have been secondary flows as well happening here. We don't know, it's too early to tell. But I wanted to show you this because it's very recent research, and it's yeah, something that, of course, the cantons in Switzerland and also other places are very interested in. Okay, this is my last slide, just to tell you a little bit of my future work, and also what, yeah, maybe could be a point of collaboration with you guys as well. We want to improve our model, the one I showed you today, to better capture cohesive and compressible materials. One step that we have to do is to improve our hardening loss so that we can better reproduce the observed density variations. And another final thing is that is very relevant in snow is when we have a time-dependent cohesion. So in snow, we have ice grains, right? And when ice grains come into contact with each other, they tend to like stick together. They tend to like freeze together. And so that can lead to very interesting mechanisms, as you can see in this uniaxial compressive experiment. I don't know if it's so visible on this screen though, but you see here, there's this band propagating down, and then it reflects at the boundary, and then it starts propagating up again. So it's a compaction, it's an oscillating compaction band, it's called, just because you're compressing from the top here. And this can really be attributed to the fact that you are breaking and healing those ice bonds in the snow microstructure. So yeah, that's it. Thank you very much. I hope you enjoyed this talk and look forward to your questions.
Thank you. Do you have any question?
Thank you, Lars. For example, in your last movie, how many parameters you have, and do you need a lot of tuning before it succeeds well?
Yeah. That's an excellent question, and it's also why we are developing these kind of models, because a lot of the parameters are measurable and physical. So we have our elastic parameters, so our Young's modulus and Poisson ratio. This will typically not affect this flow as much because we are mainly plastic, at least in this kind of event, right? So having those parameters precise would not really matter too much. And then we have the plastic parameters. So we have the compressive strength and the cohesion. And then we have the sort of mu rheology parameters. So mu1, mu2, and the reference inertial number. Yeah. And so, you know, a lot of these parameters, I think, are something that you can sort of deduce from also basic geomechanics tests, triaxial tests, and so on, if you know what the material is. Yeah.
Thanks. I have a question, actually a couple questions, but the first one is on the hardening laws. So you've mentioned, I think, isotropic hardening. Is snow also material that behaves with kinematic hardening?
That's a good question. As far as I know, this is a pretty good hardening law because it's really driven by the volumetric deformations in an isotropic way, and then we have the beta parameter to tune this. Whether you can have a kinematic hardening law, perhaps, yeah, it's a good question. Okay. I think this is also a point of future research, how we can develop better hardening laws. Yeah.
Right. And the second question would be on you mentioned that microstructure for snow can evolve. So you showed that it evolves during a test, but also like over time. Do you have a way of including this to have like a time-dependent friction or something like this in your modeling models?
The rate-dependent friction?
No, time-dependent. So like just leaving some snow at rest will change its properties just by being there.
Yeah, exactly. So this is exactly what we are thinking in terms of this thing. You know, how can we include, for example, time-dependent cohesion? That over time you leave snow, the ice grains are going to melt together, they're going to heal. So this is exactly this point. If friction, I mean, this is more of a question of cohesion. If that also relates to friction, I'm not sure if that's maybe different story.
Like state-dependent friction is typical of geomaterials.
Yeah.
I was thinking maybe snow can be affected by that as well.
Yeah, but then I'm thinking, you know, if you have a microstructure, then you have to break it first, and then sort of the friction becomes relevant. Yeah.
A very interesting and impressive simulation. My question is about the modeling part. All the models that you consider, the K-Prager model or Kamkle model, are only based on the two first invariants of the stress tensor.
Yes.
And it is well known for granular material that the third invariant, the load angle, can play also an important role in some situation. For instance, for the occurrence of shear bands in the granular matter. So my question is, do we need really this or not, in fact? If you need to improve the model by implementing the third invariant.
Yeah, no, that's an excellent question. But all of these models that I showed you were assuming that we can formulate our models just with the help of the two first invariants. Would be great to also include the third invariant, but then you have a more complex model, you have more parameters. So
maybe for the computational side, it can be more complicated. A second question is about the simulation. You don't talk about the interaction between the fluid and the granular part. In several situations, I think that you have some saturation of the granular matter. So do we take this into account or not?
yeah, you mean if you should take into account saturation of a liquid phase, for example. Yeah. For a snow avalanche, this is not so relevant. For Blatten, I think it's very relevant. Yeah, depends on your problem.
For the snow problem, there is no need to have a cooked problem.
To have a
for the snow problem, there is no need to take into account this saturation.
I don't think that would be very relevant, but yeah.
Okay, thank you.
Is there any other question? Okay, maybe a last question. We can chat with Lars.
Thank you for talk. I'm not an expert, so it's going to be a very general and technical question. The simulation that you showed, what is the computational costs of those simulations? Are they kind of cheap, or they take weeks to run?
Yeah, I mean, that of course is a good question, and it will depend on also what infrastructure you have and how many particles that you are simulating. I think in terms of the Blatten simulation, we're talking about a few hours, and I don't know how many. We have close to 1 million particles or so. So it's not the biggest simulation. We also have simulations that last a week or more. So it really depends. And it also depends, because we're using an explicit method, it also depends on the parameters, actually, because the Young's modulus will affect your time stepping.
Okay.
So yeah.
So is that something that you typically run on supercomputers, or?
You can, yes. We usually buy semi-expensive workstations. Our code is just parallelized on shared memory with Intel TBB or OpenMP. So yeah, we don't really do supercomputers.
Okay.
Yeah.
Thank you.